So let me share this screen first. So, is it visible? Okay. So we will concentrate towards understanding the dynamic CMOS circuit, but before moving into dynamic CMOS circuit diagram, let me just briefly mention that for static or steady state circuit, which we have learned so far, we were only dealing with static or steady state values at the inputs and corresponding output values. So we were not at all concerned about the transition in potential, how the potential value transited from 0 volt to 5 volt or 5 volt to 0 volt, or logic level transitions. During the transitions, what is the situation of the circuit, or what is the condition in how the circuit responds. That was not our matter of concern while we studied the steady state circuits or static circuits. Whereas in dynamic circuits, every aspect will be taken care and taken into account. Also, there will be very significant changes in terms of the design of the circuit, where we will be introducing the clock signal. So there will be a clock signal based on which the circuit will operate, and also we will take into our consideration the one of the capacitive effects which is felt within the circuit called parasitic capacitance. Parasitic capacitance. What is parasitic capacitance? This is not a capacitor. This is a capacitive effect. This is a capacitive effect felt at different nodes of the circuit. Different nodes of a circuit. So make one thing very clear within your mind, that parasitic capacitance is not a capacitor which you have introduced within your circuit. This is not a component level capacitor. So this is not a capacitor as a component. Rather, it is a phenomena beyond the control of the designer. Of the circuit design. So this phenomena or the capacitive effect will be considered while we deal with the operation of any dynamic circuit, mind you. So parasitic capacitance, the significance of parasitic capacitance is we will be considering this capacitive effect while we analyze the operations of any dynamic CMOS circuit. So dynamic CMOS circuits are quite different with that of static CMOS circuit, because it has introduced the clock signal. That is the most vital difference in terms of your visuality of a capacitive of a dynamic CMOS circuit and static CMOS circuit. In static circuit, we did not have any clock signal. Whereas, and another difference is the effect of parasitic. So let us introduce the first and the most basic kind of dynamic CMOS circuit. So there is a CMOS transistor at the top, connected to the clock signal. Also, other end is connected with the biasing power supply of plus VDD. Then we can provide a driver transistor over here, say with the input Vin. We have another NMOS transistor at the bottom. So these two transistors gate terminals are connected with one another, and you provide a clock signal here. So you denote a clock signal by this symbol phi. You ground the last CMOS transistor. Consider the output of the circuit from an intermediate node between the topmost PMOS transistor and the driver NMOS transistor, which takes the input of Vin. And you consider the output over here, Vout. But we will not neglect the parasitic capacitance effect at the output node. So you do not draw it with bold lines. Rather, this capacitor is drawn using dotted lines. That is the symbolization of parasitic capacitor. So two parallel plates, they are bolded, but the connectivity is in a dotted fashion. So that it represents this is not a component level capacitor, rather a parasitic capacitor. What kind of output node parasitic capacitor? COP. Output node parasitic capacitor. So this is the most basic dynamic CMOS circuit. And let us see, as because it is a single input circuit, we can eventually conclude that this is nothing but an inverter circuit, a single input, single output circuit. But how it operates, that's the most interesting feature. So, of course, if you are using this in a digital logic realization phase, so Vin can take two potential values, 0 volt or plus VDD. So Vin potential values can be either 0 volt, Vin corresponding Vout. So Vin can be either 0 volt or plus VDD volt. So but before moving into this truth table, we also need to consider this clock signal. Now, what is a clock signal? Clock signal is basically any kind of electrical signal with a periodicity of pulsating trend. So there will be pulses or square waves. So there will be a periodic square wave coming one after another. The frequency is having a frequency based on the inverse of the time period. So this is basically a clock signal. So it will be toggling between a 0 logic value and a 1 logic value, or 0 volt and plus VDD amount of potential in amplitude. So 0 and 1 represents, of course, plus VDD and 0 in terms of voltage. So here it will be toggling between 0 logic value and 1 logic value, or in other words, the amplitude will move from 0 volt to plus VDD amount of potential. So usually in most of our VLSI circuits today, we use the biasing potential of plus 5 volts. So VDD equals to 5 volts. That's a different issue altogether. But the clock signal will toggle like this. in a periodic fashion. So when the clock signal is in a low state, when it is in a low state in the first half time period T/2, it is in a low state. So when it is in a low state, what happens for this CMOS transistor? So we name it as TP. This CMOS transistor switches on, and this NMOS transistor switches off. That is the logic we know. Till so far we have studied the CMOS level circuit. That when phi equals to 0, you provide at the gate terminal, right? Where you can use the concept of static CMOS inverter, where you have used that the input potential can be either low or high. That low input potential is provided at a gate terminal of a CMOS transistor, whatever. So when you provide a low logic at the gate terminal of the CMOS transistor, the CMOS transistor switches on, whereas the NMOS transistor switches off. Now, as the NMOS transistor switches off, this lower portion of the circuit remains in a non-conductive state. So it is not in a conductive state. Whereas this portion of the circuit, the upper portion from the output terminal to biasing potential, remains in a conductive state. Now, there is a capacitive effect felt at the output of the circuit, which is called as COP. So ultimately what happens is COP capacitive effect, or the parasitic capacitance COP. Parasitic capacitance COP draws a substantial amount of current from the biasing potential towards it, charging up this parasitic capacitance. So as because TP is switched on when phi equals to 0, during that phase, that means during this half time period capital T/2 of the clock signal, the biasing potential inhibits the current flow through this direction, which is being denoted using this blue arrow, charging up this output node parasitic capacitor. So this charging of parasitic capacitor will continue till the potential across the capacitor reaches the amount of VDD, because then only within this conductive path both the ends will remain in the same potential and the current flow will stop. So this flow of current, flow of charging current through the TP transistor continues till you receive a output potential Vout or VCOP, that is potential across COP, that is nothing but Vout, equal to the biasing potential plus V. So what we feel that during this half time period, when phi is 0, Vout represents a high logic value, or Vout represents a potential value equivalent to equal to plus VDD, due to this charging up of parasitic capacitor. So we can segregate the circuit analysis into two phases. Phase 1, when phi is 0. So when phi is 0, charging of COP occurs through the switched on transistor TP. Is it clear, students? Tell me whether it is clear or not. Yes, am I audible?
Sir, can you
Yes,
please explain once again?
we are using a clock signal which connects directly to the gate terminal of the topmost CMOS transistor TP and the bottommost NMOS transistor. We haven't named it as yet. And the transistor which remains at the middle takes the input signal V. So this is nothing but the driver transistor of the overall circuit. Now, the TP transistor can get switched on if you provide a low logic value at the clock signal. So the clock signal is nothing but a pulsating trend which keeps on toggling between 0 logic value and 1 logic value. So 0 logic value represents a 0 volt amplitude and 1 logic value represents the plus VDD amount of amplitude for this waveform, square waveform, which is a pulse train because this square waveform is in a continuous fashion. So this is nothing but the property of the clock signal. So in the reset situation, or rather when the clock signal is in a low state, that is the first half time period, capital T by 2. So if the overall time period is denoted by capital T, if the time period is denoted by capital T, then the half time period is capital T by 2. So during this capital T by 2 amount of time, the clock signal remains in a low logic state. So this low logic state fed into this TP transistor will make this transistor switched on. Whereas this bottom level NMOS transistor, which is also connected with the clock signal, remains switched off. Now when TP transistor remains switched on and the lower level transistor, which is the NMOS transistor, remains switched off, then we can say that at least the upper portion of the circuit is conducting. We do not know anything about this transistor which takes V in input because we are not concerned with what is the input potential now. So V in can remain on or it can remain off depending on what, this transistor which takes the input V in can remain on or off depending on what is the logic given within V. We are not concerned within that, but we are sure that TP transistor is in a on state when you provide phi equals to 0. And the bottom level NMOS transistor remains in off state. That means if you divide this circuit into two parts, the uppermost part from the output terminal to the biasing potential and the lowermost part from the output terminal to the ground, then we can say the upper portion is conductive when phi equals to 0. So if the upper portion is conductive, then VDD will have a path to ground through these output node parasitic capacitors because there is an output node parasitic capacitor there at the output terminal of the circuit. So VDD will tend to discharge through this path, through this output node parasitic capacitor by charging up this capacitor. So from VDD there will be a current I drawn by this output node parasitic capacitor in this direction, which is in shown. So this current will charge up this output node parasitic capacitor. Now, how long this current will flow? This current will flow till the charge which gets accumulated across the output node parasitic capacitor displays a potential value equal to VD. Because then only for a ohmic conductor, if VA and VB becomes equal, then ultimately the potential difference VA minus VB becomes 0. Now, if it becomes 0, it will imply that the I current flowing in this direction will also become 0. So, ultimately the current flows till the potential across COP reaches the plus VDD value. In other words, what is the potential across COP? The potential from this point, one end of COP and the other end of COP. this potential difference, that is nothing but V out, because V out is nothing but you take the potential from this point and across ground. So V out and VCOP, V out and VCOP is nothing but same. So when VCOP reaches plus VDD amount of potential, then this charging current I will stop. So what happens during this capital T/2 amount of time, this charging up of output node parasitic capacitor, COP, happens. And that will dictate the V out potential or the output potential to a logic high state, or to a potential equal to plus VDD. So during this half time period of the clock signal, during this first half time period of the clock signal, there will be a full charging of output node parasitic capacitor, which will ultimately imply that you will be receiving an active high output potential at the output of the circuit. So if we can divide the circuit operation into two phases, depending on whether the clock signal is in a low state or in a high state. So the phase 1, when the clock signal is in a low state, denoted by phi equals to 0 symbolification, we can say charging of output node parasitic capacitor COP occurs through the switched on transistor TP, because TP transistor also remains switched on when phi equals to 0. So that will imply that the V out will reach a potential value equal to plus VDD. That is logic 1. Is it clear or not? Tell me. Yes? Is it clear?
Yes, clear.
Everyone? If anyone is having any confusion, you can say. Okay, so we are now studying only the half time period of the clock signal when clock is in a low state. When the clock signal is in a low state, what happens to the circuit? Now, in the next half time period of the clock signal, that we can denote by phase 2. Phase 2, that is the next half time period of the clock signal. So when phi equals to 1. So when phi equals to 1, what happens? TP transistor switches off. So when phi equals to 1, TP transistor switches off. And this transistor, so this transistor becomes off and this transistor is on. So now we can say that the uppermost portion of the circuit is in a non-conductive state because the circuit is incomplete within the uppermost portion. But in the lowermost portion, that is from the output terminal to ground, we are not sure whether the circuit is complete or not because we do not know the V in value. So now the V in value comes into picture. Now we will see that what happens when V in is 0 and what happens when V in is 1. The lowermost TN transistor is in a always on state because phi equals to 1 now. Because phi equals to 1. So V in can remain in two states, either 0 volt or plus VDD amount of potential. So either 0 logic or 1 logic. So let us consider first Vin is in a 0 logic value or in a 0 volt state. So when Vin is in a 0 logic value, this transistor which is taking Vin as an input also remains off. So if this transistor remains off, then we can conclude directly that the lower portion of the circuit which was considered now is also in an unconductive state similar to the upper portion. So if that is the situation, then what will be the output? The output which was already charged up to a potential equivalent to plus VDD retains this charge. Why retainment is there? Because it is a capacitive effect. A capacitor always retains charges. If not, it gets a direct path to discharge. Now here, the circuit which is connected with that of the capacitor is in a non-conductive state. Both the upper portion as well as the lower portion is in a switched off situation. There is no current flowing path in both the directions. So the capacitor retains the charge. So when Vin equals to 0, when Vin equals to 0 volt or it represents 0 logic, the capacitor retains the charge. So if it retains the charge fully, the potential across the capacitor remains, or VOP remains equal to plus VDD, which is nothing but the output potential. So when Vin equals to 0 volt, the output potential is plus VDD. Now coming to the next possibility of Vin or next case of Vin. When Vin equals to not 0 volt, when Vin equals to plus 5 volt. So that is the next possibility of Vin when Vin equals to plus 5 volt or plus VDD or logic 1. Then what happens? Then this transistor switches on. The transistor which takes Vn as input switches on. Now mind it, every discussion we are doing now is during the second phase of the clock signal, phase 2, when phi equals to 1. During this half time period, so the amount of time is capital T by 2 during this time also, because that also gives another half time period when phi is, when the clock is high. So during this half time period, our discussion is going on now. So during this half time period, Vin can be either 0 volt or Vin can be plus VDD. So when Vin is 0 volt, we have got the V out as plus VDD. Now when Vin is plus VDD, what happens? This transistor switches on. The lowermost NMOS transistor remains in a switched on situation because phi is 1. So the potential across COP, which was plus VDD, due to the charge accumulation over here, due to the very high density charge accumulation at the topmost parallel plate, now do get a path to discharge. Although TP is off, both these NMOS transistors which connects this capacitor on the other way towards ground is on. So there is a conductive path, and as soon as a conductive path is there, this charge will tend to discharge to ground through this path. So the discharging of output node parasitic capacitor takes. As the output node parasitic capacitor discharges, maybe after say small t1 amount of time, it discharges and there remains no charge within this capacitor. So T1 is of course less than capital T by 2, because everything is happening now within this capital T by 2 amount of time. So this discharging time must be less for this capacitor to get fully discharged. Now if this situation occurs, then what will be the potential across the capacitor? It will be 0 volt because it has discharged every amount of charge it had accumulated previously. So if there are no charges across the capacitor, if you just calculate the potential, it will be 0 volt as every charge is discharged. So what will be the V out amount of potential here? 0 volt. So depending on V in, whether V in is 0 volt or V in is plus VDD, this charge which accumulated within the capacitor in the first phase of clock signal when phi equals to 0 will either be retained or it will get discharged. That will trigger the output potential, or in other words, the output logic state. So the output logic state will be controlled by this input signal, as because this input signal can create a conductive path for this capacitor to discharge, or it cannot create a conductive path for the capacitor to discharge. So whether it creates or it do not create, depending on that, this charge across the output node parasitic capacitor will be either retained or it will get discharged. If it gets retained, V out remains in a high potential or in a higher logic state. If it gets discharged, V out moves to a transits from a high logic state to a low logic state or a lower logic state. Is it clear or not? Tell me. Tell me, is it clear or not? So when phi equals to 1, V in can be either in logic 0 or in logic 1. If V in is in logic 0, then COP shall retain charges and V out remains in logic 1 state. So why we use the term remains? Because V out will reach a potential value equals to plus VDD, that is logic 1. That already happened in the first phase. So that logic state which happened to V out in the first phase will be remaining over here if V in is in a logic 0 state. But if V in is in logic 1 state, then COP shall discharge to ground. And V out transits to logic 0 state. So if V in is logic 0, V out is logic 1. If V in is logic 1, V out is logic 0. So ultimately we are analyzing the situation of transistor in a very transient character, where the output node parasitic capacitor do get time and path to discharge, it discharges. If it do not get time and path to discharge, it do not get discharged. So depending on whether the output node parasitic capacitor remains charged up or it remains totally discharged, the output potential varies. And this circuit ultimately gives us, or if we analyze this circuit, this gives us the logic of an inverter circuit or a NOT gate, which is a dynamic CMOS circuit, NOT gate. So tell me, students, where is the point of confusion, or if you have understood the Yes? So there are two phases of circuit operation which we have analyzed, phase 1 and phase 2. During phase 1, we are not concerned with the input potential. So we are not at all concerned with the input signal. Rather, as because phi is 0, the clock signal is in a low state, the charging up of output node parasitic capacitor occurs and the output potential directly switches to logic 1 state or a high state. So this phase 1 is also termed as the pre-charge phase. Pre-charge phase. This is called a pre-charge phase, and the transistor which remains on during this pre-charge phase, that is this PP transistor, is also called pre-charge transistor. This is nothing but pre-charge transistor. Whereas in the second phase, we are rather concerned with what is the input signal, whether Vin is in a 0 logic value or Vin is in a 1 logic value. In other words, whether Vin is 0 volt or Vin is plus VDD amount of resistor. This consideration we do only during phase 2. So phase 2 is called evaluate phase. Evaluate phase. And the transistor which remains on during this evaluate phase, this NMOS transistor is called evaluate transistor. Evaluate transistor. So this is signified by the symbol TN. It is symbolized by TE. TE. So the first transistor is symbolized by TP, the CMOS transistor. This is symbolized by TP, and the bottommost NMOS transistor is symbolized by TE or evaluate transistor, because this remains on during the evaluate phase of the clock signal or evaluate phase of the circuit. So the first transistor is on during the pre-charge phase of the circuit when phi equals to 0. And second transistor or the last NMOS transistor remains on during the evaluate phase of the circuit when phi equals to 1. Now this is nothing but the driver transistor, because the Vin potential at the gate terminal of this transistor ultimately drives the output logic of the circuit. Because depending on Vin, either the output node parasitic capacitor, which was totally charged up during the pre-charge phase, will get discharged or it will retain the charge. So for any kind of dynamic CMOS circuit, we have the pre-charge transistor at the top. We have the pre-charge transistor, which is a CMOS transistor, TP, at the top. There is the NMOS network. Taking the input signal. So for an inverter, this is a single NMOS transistor. And we have an evaluate transistor, which is the NMOS transistor, TE, at the bottom. The gate terminal of the pre-charge transistor and the evaluate transistor are shorted and connected to the clock signal. The feature transistor at other end is connected with the biasing potential. The evaluate transistor at the other end is connected to ground. And from an intermediate node between the NMOS network and the features transistor, you collect your output. And of course, there is a effect of output node parasitic capacitor denoted by this dotted line, COP, which gets charged up during the feature phase and may or may not get discharged during the evaluate phase. So how you can trigger the evaluate phase? When phi equals to active high or in a higher amplitude, and you consider the input signal, you can move into the evaluate phase and determine whether COP discharges or COP retains the charge. And thereby, it will dictate the potential value of the logic state of the output. So this is the very generic representation of a dynamic CMOS circuit, where we need these two transistors coupled, TP transistor, the features transistor, and the evaluate transistor. And both these gate terminals are shorted, connected to the clock signal. In between these two transistors remains the actual logic circuit, which is the NMOS network, that depending on the Boolean expression you have provided, you have to design the NMOS network. And the same technique which we have used for designing CMOS circuits, NMOS circuits, or static CMOS circuits, the same designing technique for NMOS network will be followed. And there will be transistors aligned within this NMOS network. Where you have provided input, you can provide inputs and receive the output accordingly. So is the operation of dynamic CMOS circuit understood? Yes or no? Yes, student? I cannot hear you.
Yes, sir.
Yes, Saurabh?
Yes, sir. It's understandable, but I need to go through it once again.
Yes, everyone needs to go through this. Everyone needs to go through the lecture. You need to go through this. I will be referring you textbooks also. So not only this particular circuit, if you need to go through any other previous lectures also, you can go through following what has been taught in the class as well as the reference books. If you need to go through more details. So for this, let me give you some names of the reference books for the topics we have discussed so far. List of reference books. McGraw-Hill edition. So for MOSFET, physics of MOS transistors, more precisely, physics of MOSFET. Initial structures and operations of MOSFET, the PMOS circuit and the CMOS inverter circuit, mind you. I have taken from integrated electronics from Milvan and Malkia. Then for NMOS circuit, CMOS circuit, integrated circuit. Come. This is also a data magazine edition. You may get a ebook also. Freely available ebooks are there for this second book, Digital CMOS Integrated Circuits by Kant. So for the static CMOS circuit, mostly I have referred this Digital CMOS Integrated Circuit, and for dynamic CMOS circuit also you will be getting in this book. So dynamic CMOS inverter or other circuit. So far we haven't moved into much variety of books, but as and when the topic approaches, maybe other books will also be referred. But here only two books we can have gone through. For the introductory classes, the PMOS circuits, MOS inverter, CMOS inverter, especially integrated electronics by Milvan and Halkier. There are plenty of books in the library, mind you. I don't know you are moving into college or not, but you can just come to college and just pick up these books from the library. There are plenty of books in the library, and I think from 1st November the library is open also. I have seen it open. You can collect the books if needed. And for dynamic CMOS inverter, which we have studied today, and other dynamic circuit we will be studying further. I will be referring to the same book. And then when we will be moving into the power consumption chapters and all other things, then there will be different references. Up to this, only these two reference books I have gone. Okay. But if you understood the lecture in clarity, then you do not need to move into books. But actually, for more details, you can always move into the reference book. But understanding the lecture is the most vital thing. So I think that you have already copied this. So you can go through it in next 1 week's time. Try to revise the whole 11 or 12 lectures which we have undertaken in this theoretical course. Because next week I will not be taking any class. So after today, maybe I will be taking the next class on 15th of November. Today is 5th of November, so you will be getting another 10 days of time to go through or revise the entire lecture. Already before this, the lecture extract has been given to you. So have you received the lecture extract?
Yes, sir, we have already received.
Okay. Thank you. This is all for
Sir,
today. Yes.
sir, we do have a request actually. If there is a opening of college on 16th November, as per the instructions of the Education Ministry, then we might need to shift into hostels and do some formalities in the college. Those are the hostelers. So it would be better if we can start the classes from 16th.
Yeah, that will be accommodated. If you need to move into hostels on 15th and all those things, and you need a 1 or 2 days gap before starting the lecture, that can be provided. PR will be corresponding that way.
Okay, sir. Thank you so much.
Okay. So thank you for today's lecture.
Thank you, sir.